In this problem, problem 6.9 in Smith & Van Ness 8th edition, we're given 1 kilogram of water with a specific volume of 1,003 centimeters cubed per kilogram. It's in a piston cylinder device at 25 degrees C and a pressure of 1 bar, and is compressed in a mechanically reversible isothermal process to 1500 bar. And then we want to determine the heat transfer involved, the work, the change in internal energy, change in enthalpy, and change in entropy. Given that we have a beta value of 250 times 10 to the minus 6 inverse Kelvin and a kappa of 45 times 10 to the minus 6 inverse bar. And so a satisfactory assumption is that the volume is constant at its arithmetic average value. If you remember back from chapter 3, we did a problem somewhat similar to this where I believe all we did was calculate the work. But here what we're going to be doing is calculating Q, delta U, delta H, and delta S. You might wonder why this is important. Just from my personal experience, if you are dealing with any kind of high pressure pumping, we use HPLC in our lab all the time, almost 24/7. And in these cases, the pumping of the liquids at very high pressure, where you're going from atmospheric pressure, one bar, to, as we say, over 1,500 bars. So, we go up to 20,000 PSI sometimes. So although we're making some big assumptions that we have an isothermal process and that the process is reversible, this is still a good way to approximate what's going on in such a process. And for these kinds of pumping applications, there are you actually have to take some of these considerations into account. So what I'm doing here is I'm using MathCAD, and some of you guys are okay with MathCAD, but some of you still aren't using MathCAD. And so what I like to do is combine this as both a problem solving session and a little bit of a MathCAD tutorial in case some of you are not quite up to speed. The first thing that I do when I open up a MathCAD file is I always change the page setup, because the default margins are 1.2 inches. I don't like that, so I always change it to 0.5 inches. So you can do that if you like. And then another thing that I want you to do when you turn in MathCAD assignments is always make sure that the problem statement is given in the MathCAD file. And so you can easily just copy and paste the problem statements from Word, excuse me, or you can do a screen capture as a picture and paste it in. So make sure you give the context of what you're solving. Now, I don't know, I'm using MathCAD 2000. The math part has not changed. There's a little bit of formatting and maybe some graphical enhancements to the MathCAD that you're using. One of the things that I have to do with MathCAD, and I've got some things already pre-written that I'm just going to drag over so I don't have to type everything all the time, is some of these odd units or different units that are not quite the SI base units. You need to define them. And so what I have is I've defined the bar as 10 to the 5th pascals, because a pascal, the Newton per meter squared, is your base SI unit. And then I can start typing in some of my given information. Remember, if I want to do Greek letters, and I try to keep the nomenclature as similar as possible to what we are using in the book. So the lowercase beta is lowercase b, and then I hit Control G for Greek, and that changes it to beta. And when I assign a value, remember you use colon, and so that'll be Shift colon. That assigns a value. That's MathCAD's little sign for assigning a value. So that's 250 times 10 superscript to the minus 6, and then I press a space bar. Press a space bar to select the entire value, and then I can type in times and then 1 over Kelvin. The base unit is Kelvin for MathCAD. And so I'm just going to drag some things over that I already had typed out on another page. So there's our value for kappa. And we know that this is a reversible isothermal compression. It deals with liquid water. And again, this is what we want to find. And so I can set up my little diagram. I have a little diagram or a little table of conditions just so I keep things straight. And so these are not too hard to set up. We go from state 1 excuse me, to state 2. It's isothermal. So I define T1 at 298, T2 is the same at 298, P11 bar, 1500 bar, and then we're given the volume at state 1, which is 1003 centimeters cubed per kilogram. So this is a first law and a second law problem. And there are a couple ways that we could look at this problem. Notice we're dealing with water, with liquid water. Probably at these conditions, this is pretty close to the saturation conditions. This is definitely not at the saturation pressure, but you know, liquid water isn't going to change volume by a whole lot. It will change a little bit. One of the ways we could probably approach this problem is to try to use the saturated liquid property tables, the steam tables for saturated liquid in the back of your book. And so you could look up volume. You know, we'd have to see, but that's one way you could approach the problem. And then of course you could look up enthalpy and entropy and internal energy, and from there you could do the calculations. Now the other way to do that, of course, is what they want you to do. And as you can see, they've given you the values of beta and kappa. And so what this means is they want you to use an equation of state for the liquid. And that's what we had back in chapter 3. And so the equation of state, this is equation 3.6. I drag that in over here. This is equation of state that we had in chapter 3 for liquids. And remember, this assumes that our values of beta and kappa are constant. Remember what we said, if it's an incompressible fluid, beta is 0, kappa 0, there's no equation of state, right? But here we have finite values. You can see they're pretty small, really small, all right? But we have finite values of beta and kappa, and so we will have a change in volume in going from state 1 to state 2. And the other thing I want to mention is they said assume a satisfactory assumption is that volume is constant at its arithmetic value. So what this means is that, yeah, we are going to calculate V2. We do know V1, all right? But whenever we have a formula that just has plain V, we're going to use the average of V1 and V2, all right? And so what we can do then is we can just put this here. We need to solve for V2. All right, the first thing that we are going to do in this problem is solve for the volume so that we can fill in our property values in this little table up here. So there's two ways you can do this in MathCAD. You can either if you're really good at doing things in your head, you can do it that way. Another thing you can do is you can actually use MathCAD to do the solution for you. And so what I've done here is I've typed this value, I've typed this formula. Let me just put it here and I'll type it again for you. And so here we have natural log of V, and then remember subscript. I like to go ahead and use subscripts. Some people just like to keep everything on the same line, but I like to use subscripts if I can. So the subscript, you type a period. So it's V period 2, all right, divided by V period 1. Now, right now, what I'm doing, you notice this equal sign is different from when I assigned a value. This is my equal sign where I'm just defining an equation. All right, I'm not calculating anything. All I'm doing is defining this equation. And so I have my left side selected. And so the way to get this bold equal sign is to press the control equal. So control equal gives you this defining equal sign. And then so it's beta, control G, times, it's asterisk, parentheses, t.2 minus t.1, parentheses, and then I want to make sure that my math is fine. MathCAD will do it, but I make sure that that entire term is selected, and then I type minus kappa K Control G times parentheses P dot 2 minus P dot 1. So, and then I can go ahead and get rid of this. Once it's selected, I can just type Control D, and that deletes the entire equation. You don't have to select it and hit backspace or delete key. Control D will delete anything when your cursor is active within an equation. So this is my equation, and what I'd like to do is to make sure I don't make any silly mistakes on a quiz or an exam. What I can do is I can tell MathCAD to solve directly for this, and so I'm going to type V2 and then my colon for equals. And then what I'm going to do is I'm going to select V2. This is what I want to solve for. I go up to symbolics, I go to variable, and I say solve for variable. All right, I solve for the variable, and you see this is what I have. This is MathCAD's solution for V2. I select that, cut it, Control X, put it in my active cursor there, and then I just paste it. Control V will get that in there. So now V2, this is an assigning equation. V2 is calculated by this formula, and then if I want to print out the value of V2, I just type V2, so V dot 2, and then just the plain equal sign. A plain equal sign. This will give you the value of V2. So there's several equal signs. There's the colon where you're assigning something. So we use that when we assign constants. We use a colon when we assign an expression to a variable. There's the bold equal sign, which is just used as a definition. We aren't actually calculating anything specifically here. We're just telling MathCAD this is an equation. And the nice thing about this is you can use MathCAD. You can go to symbolics, variable, solve to solve for any one of those variables. So if I wanted to solve for T2, I could solve for T2, and there's my T2. All right, so Control D, get rid of that, and we can, formatting is a little cumbersome, but we can get rid of that. Okay, so that's my V2. Now, notice that, where is it? V1 was given in centimeters cubed per kilogram. All right, V2, when MathCAD does its calculations, it puts everything into pretty much base SI units. And sometimes it's fine, sometimes it's kind of a pain, or it's just not quite as convenient. And so I want to keep everything in centimeters cubed per kilogram. And so the way to do that is when the calculation is done, you can click on to the right, the little cursor there to the right, and then I just enter what units I want. So I want to go from meters cubed per kilogram to centimeters cubed per kilogram. So I just type centimeters, caret, cubed, and I select all that, divided by kilogram. And so now I have my units consistent with what I had defined them to be earlier. I could have left everything in meters cubed per kilogram, but just because the volumes are specific volumes are very big, you end up with scientific notation. Maybe that's not quite as convenient or photogenic looking as you're doing the the calculations. So that is our calculation for V2. And remember, what we want to also get, we also want to get the average volume. So the average volume, we'll just call that V, is equal to V2 plus V1 divided by 2. And then I always like to put my values that I'm calculating a little bit to the right so everything's not all jumbled up. Formatting is a lot of what you end up doing with any kind of MathCAD or spreadsheet. And so we see what we have here. So the initial volume was 1,003 centimeters cubed per kilogram. Our final volume, 937. We're using an average volume whenever we need it of 970 centimeters cubed per kilogram. Now we can start calculating things. So the first thing that I would probably calculate, and with the old MathCAD, it's different for you can define specific text regions. With this MathCAD that I'm using, I just type things in. So I'm going to calculate work. All right, and so we know it's reversible. And so what does that mean? That means that work is equal to minus the integral of PdV. And if you want to, and what I would recommend is as you solve these problems and as you work these problems, that you maintain a good train of thought and document your train of thought. And so I'm going to go ahead and put in my PDV equation. So I'm going to type W, Control Enter, and then I can actually put, MathCAD has some toolbars. This is in my upper toolbar. I can pull this down, and this is my calculus toolbar. And so I've got all these little pre-formatted templates that I can use. And so just to make things look nice, I can put, click on this for the definite integral. And so my term there is minus P and dV, and this is going to go from V1 to V dot 2. All right, so that is my that's my equation that I'm going to use for calculating the work. The problem is what? Well, we need an equation of state. We need to put something in here. All right, the pressure is changing. Pressure is changing and volume is changing, and so what we're going to have to do is figure out what we put in here for our equation of state. Well, our equation of state is given in chapter 3. All right, this was the fully integrated equation of state, and this was equation 3.6, but we just need something. You can see everything here is V1, V2, T1, T2, P2, P1. We need something. We just have P and we just have V, right? Our limits are V1 and V2. We need something to put in here. So what we can do is we can go to, I forget what page it is, but it is equation 3.5. Equation 3.5 is this equation right here. It's one of the intermediates, whoops, one of the intermediate equations. That is dV over V is equal to minus kappa dP. And all this is the equation of state, the original equation of state that is valid for an isothermal process, because dT is equal to 0, right? It's isothermal, there's no change in temperature, and so we can use this, right? So what I can do then is work is equal to, let me change that to control equal, and again I'm going to, let's see, what do I want to substitute for? What do I want to substitute for? Well, the easiest way to do this is to realize I can just substitute for dV. What is dV equal to in this equation of state? dV, so I'm going to start here. dV is equal to V times minus kappa times minus dP. So I'm going to write dV is equal to, I'll put minus P times, and then minus V, I'll make that a parentheses to make that a little clearer, all right? Times kappa, control G, times V, and then that is dP. Now my limits of integration are with respect to pressure. So I have P dot 1 and P dot 2. So you see how that's made? We started with minus PdV, and what we need to do is we need to insert our equation of state information in such a way that we can actually calculate, we can do the integration for the process that was defined. So this is going to be, we could have solved for pressure, right? but that's just not convenient. The most convenient way to do this is to realize I need something for dV, right? I've got this equation for dV. I just multiply through, move the V over there, and wherever I see a dV, I just put in what this is. The minus P comes through here, and then the minus P times the minus, the two minuses will cancel each other out. So I can go through, and this is an easy enough integration. I believe you can have MathCAD integrate this, but this is an easy enough integration to where you can just say the work is equal to what? Is pressure a constant? No, we're integrating with respect to pressure. But volume, what about volume? Is volume and you know what? I've got an extra volume in there. Let me get rid of that. There. Now the volume is fixed, or is there. So let's skip to kappa. Kappa is a constant, right? So we can pull that out of the integration. Volume. What about volume? Is it constant or is it changing? Well, remember what the problem statement said at the very beginning. The problem statement said that whenever we are going to need to use volume, we can use the average of the two volumes. And again, this is, if this were a gas, we couldn't do that. But because we're a liquid and this volume change, it's going from 1,000 to 930, so it's not that much. So we can just use the arithmetic average. And I believe we actually had a problem in chapter 3 where we did this. And remember, that was the problem. That was one of the problems where the solutions in the textbook was wrong. And I posted a fix of that. So work is equal to, we'll put kappa, it's okay, Control G, times volume. That's just make sure your variables are defined consistently throughout your MathCAD document. And then that will be times the integral of P dP is P squared over 2. So that will be times P dot 2 squared minus P dot 1 squared. And so I selected that whole thing. The parentheses helps me do that. So you can put a lot of parentheses in, or you can just use MathCAD selection to put parentheses in automatically sometimes, however you like to do that. That's my equation for work. So again, remember I used the assign, so that's colon. Now I want to actually print out the value of work. And so that's work and then just plain equal sign. Plain equal sign. So it's 4,912. Does anyone know what SV stands for? I believe SV stands for sieverts. This is a relic of old MathCAD. I believe old MathCAD was originally designed for primarily electrical engineers, and this is some archaic electrical engineering energy unit. I don't like sieverts. I don't want to see you have, if your new MathCAD is doing this, hopefully it won't, but anyway, if you are using an old version of MathCAD that's doing this, go ahead and change it, because chemical engineers just don't work in sieverts or whatever the hell this is, SV is. And so I'm going to change it to joules per kilogram. So I just select and MathCAD. So a sievert is a joule per kilogram. What about the sign on this? So remember, we had the two negative signs cancel, give us a positive sign. The pressure P2 is greater than P1. So we're doing a compression that's a positive work value, and the sign checks. All right, so we're doing work on the system. Energy is flowing into the system by work, and so we have a positive value of work. All right, so that is the calculation of work. Now what we have to do is we have to calculate enthalpy and entropy and internal energy changes. So if you look at page 215, you can see that we can calculate enthalpy and entropy changes, and I'm going to pull this over so I don't have to spend a lot of time typing everything out. And so what you have here is the equation information for entropy change. So ds is equal to, and again, this is because temperature is constant, minus beta times v dp. Beta is constant. Remember, v we can treat as constant as the average, and this is dp from p1 to p2. We don't have to do much of anything, right? And so we can calculate delta S just by simple integration. Delta S is going to be minus beta times V times P, or evaluated from P1 to P2. So this is our equation. So I like to keep my notation consistent, even though sometimes it's a pain. So capital delta will be capital D, Shift D, Control G. So again, some people like to actually type out DELTA with a capital or lowercase, but I just go ahead and stick with that. And so if I want to then type out actually display, so delta, Control G, S, and then just plain equal sign, that is minus 36.362 meters squared per second squared per Kelvin. Again, MathCAD is putting everything into base SI units, not very useful for chemical engineers. So I'm going to kilogram Kelvin, and you can see it does the change automatically. One of the things, what if I made a mistake? What if I thought that the units were joules per Kelvin? So if I do joules per Kelvin, what is MathCAD going to do? MathCAD's going to fix it for me. It's going to put the per kilogram in there. So that's one of the other reasons why, if I were you as a student and didn't want to be making silly mistakes on quizzes or exams, this is why I think it's good to use MathCAD. The only thing is if you rely too much on MathCAD for doing your units, sometimes you may forget to do units because everything's always being done automatically for you. So just, use it, be careful. You can see, what if I thought, even if I just were really dumb, as an Iowa State student, I've just put joules. Voila, it fixes it for us, all right? So anyway, that is our delta S calculation. Delta S is negative. Does that make sense? I think it does. If you think about, we're doing a compression, so you're actually limiting, and it's maybe not from our classical thermodynamic sense in this chapter, where entropy is always related to, or almost always related to how heat flows. But if you're thinking about entropy in from the molecular standpoint, when we're doing a compression, we're giving our molecules, our liquid water molecules, less area, less volume to move around in, and so that's going to impose more order, if you want to think of it that way, on our system. So that is our entropy calculation. Then we can use the equation on the same page. This is our enthalpy calculation. So dH is equal to integral from P1 to P2, 1 minus beta times T times V dP. So beta is constant. T, this is isothermal process, so T is constant. And remember, we're assuming V is constant at the average volume. So again, save some time so we don't have to type everything. We have our delta H, we just integral of dP is P. So now it's 1 minus beta times T1. One of the things, I didn't just put T, I put T here, but here I have to put T1, right? Because I defined T1 at the very top as my temperature. And I set T2 is equal to the same temperature. So anyway, we get our delta H calculation of 1.346 times 10 to the 5th joules per kilogram. If I wanted to, I could MathCAD, this version of MathCAD does not have kilojoules as a base unit, so I could define kilojoules as 1,000 joules. And then if I wanted to, I could change the units to, oops, kilojoules per kilogram, and there I get my answer. So for internal energy, what do we do for internal energy? Well, there's two approaches that we could take for internal energy. The first approach, I got some stuff typed out here. Let me move it over. First approach, we could use equation 635. All right, equation 635 says du is equal to beta over kappa times T minus P dV. So that's what our equation of state reduces to for this state where we have an isothermal process. And so what we need to do then is we do just like we did for work. We need to substitute in an equation of state information into this canonical equation. And so we can use the same thing that we had before. dV is equal to minus kappa V dP. So this was equation 3, whatever it was, up above. We make that substitution, so this term stays the same. All right, this just gets copied directly down, and where we see dV, we put in minus kappa times V times dP. We can then integrate this. All right, we integrate this from P1 to P2. We do that, you should be able to do the integration yourself. So this is, so kappa V, sorry, this is expanding things out. I skipped a few steps, but what we get is we are integrating P from integral dP this is where the P squared terms come from, and then this is a constant term. So when we integrate that, that's integral of dP is just P. And so we get P2 minus P1 in this term, P2 squared minus P1 squared over 2 in this term. And we do our delta U calculation. Our delta U calculation is minus 5,924 joules per kilogram. Again, if I want to change it to kilojoules per kilogram, that's great. There's another way you could have done this part, and I believe this is the way the solutions do this, your publisher solutions, is you could use the definition of enthalpy. The definition of enthalpy, remember, is H is equal to U plus PV. And so delta H is equal to delta U plus delta PV. And so in this case, we already know what delta U is, we solve for delta U and just rearrange things. And what we have here is, if you remember, there's two ways that you can treat this delta PV. It can be P times delta V plus V times delta P. That doesn't make sense for this problem because P is changing and V is changing. And so when you expand this, this delta PV is P2V2 minus P1V1. So we move the delta U onto one side, and then we have delta H minus delta PV, so minus P2V2 minus P1V1. And if we do that calculation, we get minus 5,926 joules per kilogram. You can see the previous calculation we did, we got 5,924 joules per kilogram. So that's pretty close. Which one's closer, who knows? We're making some big assumptions for everything that we're doing here, in that we're assuming here, for example, that the volume is the average. And that is probably, I guess that would probably be a bigger assumption than what we have here, because here we're actually using the volumes that we actually calculated. So assuming that original equation state was accurate, beta is constant and kappa are constant over this range, then maybe this value is a little more a little more accurate. But again, we're dealing with equations of state, and so there's probably a little bit of error along with everything. So now the last thing we can do is we can calculate Q, and this is just from the first law, and this is just old hat now. We just have our first law. Again, delta U is defined as Q plus W, rearrange. We now have solved for delta U, we solve for for W, and we just plug that in, and we get Q is equal to minus 1.084 times 10 to the fourth joules per kilogram. So that's our answer. These numbers all should make sense. So we're losing heat in an isothermal compression. We're also losing internal energy. We're gaining enthalpy. We are decreasing entropy. We have positive work done. The volume 2 is less than volume 1. So everything in this seems to be internally consistent and makes sense. This is kind of a simple form of how to use MathCAD. There's not really anything that advanced or complex. The reason I like this is because if you were to try to type this in Microsoft Equation Editor, it'd just take a heck of a long time to do this. So you can document your solution process relatively well. And so when you're working quizzes and exams, I want you to be able to do that. You can type in some explanatory text. Make sure that your variables are defined clearly. One of the things, for example, there's some things that you have to be aware of is that MathCAD has certain things. For example, we had defined work as W, but work is also, W is the base unit and the default unit for electrical energy, the watt. And so if I actually went up to the very top of this before I've calculated any work, and I type W is equal to 1 watt. So what that means is that if I were using, for example, if I were doing this in heat transfer, where joules per second is a watt, or for an electrical engineering physics problem, I would not want to use W as a variable. If I have a heat transfer problem and I am calculating work, it's going to really screw me up if I use W as my variable for work or whatever it is I'm going to do, because MathCAD will always think that is a watt. Another thing about MathCAD is gram is GM, because G, what is G? G is our acceleration due to gravity. So there are a few of these things that are going to creep up on you as you go through MathCAD, and a lot of this you just got to learn by doing. You'll run across these. If I, for example, if I screw up my syntax and I put just T in here instead of T1, it's going to give me an error. Right? These errors may not be very useful. It says the units in this expression do not match. So that's not particularly useful, but what that means is there's something in here that, and it's in this term here, that is wrong with my expression, and so then I can just click in there and type T1, and then I'm back to where it is. So that is the solution of problem 6-9, I believe. Yep. And a little bit of a tutorial of how to use MathCAD.